Hi, my name is Joe, and along with Caden, Raul, Paul, Sean, and Tim, we are Team 5. We are looking at the analysis of the Dayton 6Z846 drill press vise. Drill press vices can be bought in most hardware stores, as well as bought directly from tool and equipment retailers. The primary customer group defined for our product was machinists and machine shops, who use vices professionally, and then the secondary customer group was defined as hobbyists who use the vice occasionally to secure parts for home projects and such.
Here we see an exploded view of the drill press vise assembly, along with labeled part numbers and names that we will reference throughout the rest of this video.
To ensure we have a comprehensive understanding of the drill press vise function, our team performed a functional analysis system technique diagram to determine the why and how relationships that connected the functions of the device. Taking a look at our diagram, we determined that the primary function of the device is to hold components that are to be drilled. In order to hold the components, the device must be able to both secure and release the components. Securing the component must be done by maintaining a consistent grip force and by preventing motion of the component while being drilled. In order to release the component, the grip force must be controlled to slowly release the part from the vise. Releasing the component must also be done by allowing motion. Secondary functions of the drill press vise include assuring dependability and convenience, enhancing the product, and pleasing the senses. In order to assure dependability, the product needs to reduce any slipping that may occur to prevent misaligned holes being drilled. The drill press vise itself must not also vibrate so as not to cause misalignment of the component relative to the axis of the drill.
The first assembly sequence installs the sliding jaw onto the base first, and then the vise screw subassembly afterwards. However, the second assembly sequence details the opposite. The vise screw subassembly is installed first, which provides better access to installing the collar and key, since the sliding jaw would not be in the way yet. Sequence 1 outperforms Sequence 2 in ease of transferring and handling, because handling the base and vise screw together while installing the sliding jaw would be more difficult than handling the base and sliding jaw close together while installing the vise screw. However, Sequence 2 earned a higher score of ease of locating parts, ease of fastening and joining, and ease of assembling in parallel, because the user would have more room to install the collar and key compared to in Sequence 1 where the sliding jaw would be installed first. Both sequences tied for ease of testing subassemblies because they both accounted for the same two subassemblies to be assembled similarly.
This is our bill of materials for a bench vise. The assumptions that we made were that there will be a production volume of 10,000 units, and also in estimating material cost, we assume that there would be 20% wasted material based on the dimensions of the CAD drawing shown earlier. The total estimated price came out to be $36.96, which is about 53% of the expected retail value of our vise.
To determine the impact of a potential redesign of the vise, a function component mapping matrix was generated. If a component helps the overall assembly realize a function, it is marked with an X in the matrix. Using the function component mapping matrix and the bill of materials, parts that are candidates for redesign can be determined. The matrix shows the importance of a part, while the bill of materials shows a component's cost. Having a high importance and low cost is ideal. The combination of high importance and high cost results in a need for redesign, while having low importance results in elimination or combination of parts. The jaw plates are subject to a potential redesign because of their high cost. They carry out the functions of preventing motion, preventing vibration, and pleasing senses, giving it a high importance. The jaw plates are currently made out of brass, but might be able to be made out of cheaper material and still accomplish their current functions. Another potential redesign would be to consolidate the vise screw, rod handle, knob, and pin. These parts have a low cost, but individually lack importance as they carry out similar functions. By consolidating these into one part, time and money could be saved creating this vise without sacrificing product function. Another component that could potentially be redesigned is the sliding jaw. This component has a high price and a high importance, carrying out several functions. The jaw has a feature that interacts with the sliding key, jutting out below the clamp part. By removing this feature, the sliding jaw could be made with less material while still functioning as intended.
All functions in the function component mapping matrix were classified in one of two categories. Being that we're dealing with a product family design, we are dealing with the differences for each customer group, which are prevent motion, please senses, and prevent vibrations. In the function component mapping matrix, a part that is associated with the functions pleasing senses, prevent motion, and prevent vibration is the jaw plate. Furthermore, in looking at the bill of materials, the jaw plate is an inexpensive component in absolute terms that, if modulated, can provide a benefit to the customer by providing additional utility of the vise without further major design considerations. The additional utility to the vise would come from varying abilities of each different jaw plate. The ability of properly attaching and or milling an object on the vise depends on the geometry and material properties of the jaw plate holding the object in place.
For the primary customer group, factory workers and professional machinists in machine shops that use drill presses for a variety of specialized products, shapes, and sizes, it's advantageous to have multiple vise grips of varying jaw plate shapes and textures that better support and secure the workpiece when making professional machine cuts. That is why we designed 4 different variations of the jaw plate to differentiate between the functions more important to professional machinists and secondary customers who are hobbyists who use a drill press for smaller projects and don't need the level of precision. Based on the original assembly sequence, we created this product family assembly diagram, where the branches are product variants and the nodes represent the addition of components. With the 4 variations of jaw plates, each branch of the assembly tree requires the assembly of all the remaining components. We then modified the assembly sequence in order to take advantage of delayed differentiation. The jaw plate is now assembled last, so cost is reduced now that only 1 production line is needed for the assembly.
The primary product totaled a score of 153 based on 5 major components of ease of assembly. In comparison to the primary product, the secondary product scored a 156, which is a slight increase in the ease of assembly when the product is differentiated at the end of the assembly process.